Hello sir, my name is Rikiraj Baishya. My roll number is MEB18019. I am going to explain the assignment question and the solutions. Question 1. A hydraulic turbine is designed to produce 26.845 MW at 95 RPM under 15.24 of head. Laboratory facilities are available to provide 4.7572 foot of head and to absorb 37.285 kW from the model turbine. Determine A. The appropriate model test speed and scale ratio. B. Volume flow rate assuming efficiency of 86%. So we have given the data for prototype. Power of prototype P equal to 26,845 kilowatt. Head 15.24 foot, that is 4.64 meter. Rotational speed N equal to 95 RPM for model. Power 37.285 kilowatt. Head is 4.372 foot, that is 1.39 meter. NM is asking question and it efficiency is given 86%, that is 0.86. By using Buckingham Pi theorem, we get a dimensionless parameter called power coefficient, and for both model and prototype we equate the power coefficient, that is PP by NP cube dP to the power 5 equal to PM by NM cube dm to the power 5. From here we find dm by dP equal to PM by PP 1 to the power 1 by 5 into NP by NM to the power 3 by 5. We put the value of PM and PP and we find dm by dP is equal to 0.268 NP by NM to the power 3 by 5. It is equation number 1. Again, by equating head coefficient, that is also a dimensionless quantity. For both model and prototype, we equate it GHM divided by NM square into DM square is equal to GHP divided by NP square into dP square. From here, dm by dP is found as HM by HP to the power 1 by 2 into NP by NM. Putting the value of HM and HP, we get dm by dP equal to 0.547 into NP by NM. It is equation number 2. From equation number 2 and equation number 1, we get 0.268 NP by NM to the power 3 by 5 is equal to 0.547 into NP by NM. From here, NP by NM we found as 0.168 and NP is given as 95 and we get NM is 565.476 RPM. B. Scale ratio, that is dm by dP. We put the value of NM in equation number 2 and we get dm by dP is equal to 0.092. Model efficiency is output power by input power, that is PM by rho G HM into Q. From here we can find Q. PM is given, rho is density of water, that is 1000, G is 9.8 meter per second square and HM is given. So from here, putting the values of all the values, we get Q as 3.173 meter cube per second. Now come to second question. In second question, we have given condition at inlet of nozzle of Felton wheel are P is equal to 48.2633 bar and P velocity, that is P is equal to 24.14 km per hour. The Z diameter is D is equal to 19.05 cm and nozzle loss coefficient is equal to 0.04. The wheel diameter is D is equal to 2.44 meter. At this operating condition, the hydraulic efficiency is 0.86. Calculate power output, the normal operating speed, the approximate running speed, the torque at normal operating speed, and the approximate torque at zero speed. We have given the data, that is pressure at inlet 48.2633 bar, that is 4.82633 megapascal. D is given 2.44 meter, small d is 0.1905 meter, nozzle coefficient, that is 0.04, efficiency is given 0.86 and velocity at inlet is 24.14 km per hour, that is 6.70 meter per second. Now at the inlet and at the outlet of nozzle, we apply the Bernoulli's theorem. We get P naught by rho z plus P naught square by 2z plus Z1 is equal to P1 by rho z plus P1 square by 2z plus Z2 plus its minor, that is minor losses. Now since Z1 is equal to Z2 at same height in nozzle is horizontal, so inlet section and outlet section are at same height, so Z1 and Z2 are cancel out each other, and in gauge pressure, atmospheric pressure is 0, so P1 is 0, and minor losses we know that is K P1 square by 2G, as K is nozzle coefficient. We put the value of K, that is 0.04 P1 square by 2, and from this equation we get we put the values all given, that is 4.826633 into 10 to the power 6 divided by 10 to the power 3 into 9.81. P1 is 6.70, it is given in question, divided by 2 into 9.81 is equal to P1 square divided by 2 into 9.81 plus 0.04 into P1 square by 2. Here unknown quantity is only one, that is P1, and from this equation we get P1 is equal to 96.564 meter per second. Now flow rate is Q is equal to A1 into P1. Given diameter is 0.1905 meter, that is A1 is equal to pi by 4 into 0.1905 meters square into 96.564, that is 2.752 meter cube per second. Now total head loss. Total head loss is calculated when water enters the inlet of the nozzle and it comes out from the outlet, and total head loss is happens in between inlet and outlet. So total head loss, that is formula is P naught divided by rho z plus P naught square by 2z. Here P naught is given as 6.70, P naught is given 48.26300 divided by 10 to the power 3 into 9.81. From here we get net head loss that is 494.273 meter. Again hydraulic efficiency is given, that is 0.86, and efficiency is power output by power input. Power output is asked and power input is rho z q h net. From here we found power output as rho z q h net into efficiency. Rho is density of water, that is 10 cube, z is 9.81, q is 2.752, h net is 494.273, and efficiency is 0.86, and power from here we get power output as 11.46 megawatt. And in B, for maximum efficiency, U by V1 is equal to half, but practically it varies from 46% to 49%, so we take U by V1 is equal to 0.46. So U is equal to 0.46 into V1, and V1 we found here, so 0.46 into 96.564, that is 44.419 meter per second. And we know U is pi d n by 60, and from here we found n, that is 60 into U divided by pi d, and d is 2.44 meter, that is given in the question. From here we found n is equal to 347.680 rpm. Now runway speed. At runway speed, the tangential velocity u and the striking velocity v1 are equal, that is 96.564 meter per second. So at runway speed we found that is nr is equal to 60 u divided by pi d. Here u is 96.564 2.564 and D is 2.44, that is given in the question. That is NR is equal to 755.83 RPM. Now question D, that is we ask torque operating speed. So it is the outlet velocity diagram. This is P2, that is outlet velocity. U is tangential velocity, and here beta is 15 degree. Beta is runner van angle. PR2 is relative velocity, and practically angle of deflection is 165 degree. If angle of deflection is 165 degree, that is then beta will 180 minus 165, that is 15 degree. Now we know torque is force into perpendicular distance, that is force is rho q v1 minus u 1 plus k cos beta into d by 2. R is d by 2. And from previous we know u is equal to 0.46 v1 and k is 1 since there is no friction present. So we get torque is equal to rho is 1000, q is 2.752, v1 minus 1 minus 0.46, v1 is common, 96.564, 1 plus k is 1, cos 15, that is beta, runner van angle, d is 2.44 divided by 2, that is torque is equal to 344,179.02 Newton meter. Now torque at zero speed, that is when u is equal to 0. In previous formula, when we put the value of u is 0, then we find the value of torque as rho q v1 minus 0 1 plus cos 15 2.44 by 2. Putting the all values, we get 637,368.55 Newton meter. Now come to the question number 3. The reaction turbine at Niagara Falls are of the Francis type. The impeller diameter is 4.5 meter. Each turbine produces 54 megawatt at 107 RPM with 93.8% efficiency under 65 meter of net head. Calculate the specific speed of these units. Evaluate volume flow rate to each turbine. Estimate the penstock size if it is 400 meter length long and the net head is 83% of the gross head. Assume suitable data if necessary. Here in this question given, capital D, that is diameter is 4.5 meter, power is 54 megawatt, that is 54 into 10 to the 6 watt, rotation speed n is equal to 107 rpm, that is 1.3783 revolution per second, head is 65 meter, efficiency is given 93.8%, that is 0.938. Now NST, that is first we have to calculate specific speed of this unit. Specific speed is NST is equal to n p to the power 1 by 2 divided by s to the power 5 by 4, that is 107. 54 into 10 to the power 3, it is in kilowatt to the power half divided by 65 to the power 5 by 4, that is 134.722 rpm. B, we know efficiency is power output by power input, that is power by P, rho, and power input is rho Z QH. From here we can find Q is equal to, we put all the values of eta, P, rho, C, H, find, and we find the value of Q, that is 90.28 meter cube per second. Now penstock size. Net head is 83% of gross head, that is H is equal to 0.83 into Hg. Hg is gross head. So net head is given 65 meter, and from here we found gross head is 78.312 meter, and we know net head is equal to gross head minus frictional head loss. From here we can find the frictional head loss, that is 13.312 meter. And from the Darcy-Weisbach equation, frictional head loss is equal to FL q square divided by 12 d to the power 5. So from here, putting the value of L and Q, and also from Modi's chart, we can find the value of F if the Reynolds number is 3 into 10 to the power 5. So all the values put here, that is F is equal to 0.044, length is given in the question, that is 400 meter, Q is just found here 90.28, D is given that is 13.312 here. Oh, sorry. So from here we found D is equal to, D is have to find, that is 3.8962 meter. Now come to the question number 4. A propeller turbine has been designed to develop 22,000 kilowatt under a head of 20 meter wheels turning 150 rpm. The relevant data is hydraulic efficiency 95%, overall efficiency 88%, outer diameter is 4.5 meter and diameter of hub is 2 meter. Determine runner angles at the hub and at the outer periphery. Here given data is power, that is 22,000 kilowatt, head is 20 meter, rotational speed, that is 150 rpm, and for we know that propeller turbine is Kaplan turbine, and for this P omega 2 it will be 0, and total overall efficiency is 88%, that is 0.88, hydraulic efficiency is 95%, that is 0.95, and outer diameter is 4.5 meter and hub diameter is 2 meter. For propeller turbine, we know that Pf1 is equal to Pf2 is equal to Pf. Now come to velocity diagram. This is inlet velocity diagram. P1 is striking velocity, Pr1 is relative velocity. This will be tangential velocity of the turbine, that is U1, and from this beta 1 is runner fin angle. So from here we can find tan 180 minus beta 1, that is this angle. Tan 180 minus beta 1 is equal to perpendicular by base, and perpendicular is Pf1, that is Pf1 divided by base, that is this one, U1 minus P omega 1, and this is outlet velocity diagram, and from here we can find beta 2, tan beta 2, a perpendicular by base, that is Pf by U2. Now for outer periphery, efficiency is U1 P omega 1 Z H net, since P omega 2 is 0. So from here P omega 1 we can find that is efficiency into Z into total head divided by U1, and we know U1 is pi D naught n by 60. Here D naught is outer diameter, since we are talking about periphery, outer periphery, so here diameter is taken as outer diameter, that is 4.5 meter. So from here we putting all the values here, hydraulic efficiency Z H net we found P omega 1, that is 5.273 meter per second. Now overall efficiency is given. So overall efficiency is nothing but it's a power of shot divided by power of input. It is output power given in the question, that is 22,000 into 10 to the power 3. It is in watt, so rho z, and power output is rho z is net into Q. From here we can find Q, and rho is 1000, z is 9.81, H net is 20, and efficiency is 88%, that is 0.88, and from here we can find Q is equal to 127.42 meter cube per second, and also Q is area into velocity, and for Kaplan tip Q is pi by 4 into d naught square minus dh square. Here dh is half diameter, d naught is outer diameter, into velocity. From here we can find Pf, that is 4q divided by d naught square into dh square. Putting all the values, Q, d naught, dh, we found velocity as 9.98 meter per second. Now it is this formula is found from the velocity diagram. 10 beta 2 is equal to Vf by U2, that is 9.98 by U2 from here, and also U2 is pi d naught n by 60. Here d naught is 4.5, that is outer diameter, since we are talking about outer periphery. By calculating this, 10 beta 2 is equal to 9.98 divided by U2, that is 3.14 into 4.5 into 150 divided by 60 is equal to 0.282. From here, beta is found as tan inverse 0.282, that is 15.748 degree. Again for inlet, tan 180 minus beta 1 Vf by E1 minus P omega 1. It is from here, tan 180 minus beta 1 is equal to Pf is found 9.98, E1 is 3 pi dn by 60. Outer, it is talking about outer periphery, so we take d naught is 4.5, so 3.14 into 4.5, and n is 150, that is given, divided by 60 minus P omega 1 minus, that is 5.273. So from here we can find beta 1 is equal to 161.634 degree. Now 10 beta for the hub. 10 beta 2 is equal to Vf by E1. Since we are talking about the hub, so we take the diameter 2, that is hub diameter. Vf is found 9.98, E1 is pi dn by 60, so pi into 2 into 150 divided by 60, that is 0.636. From here, beta 2 is equal to tan inverse 0.636, that is 32.456 degree. And also for inlet, tan 180 minus beta 1, that is Vf by E1 minus V omega 1, that is 9.98. We take 2 because we are talking about the half, so we take half diameter, that is pi into 2 into 150 divided by 60 minus 5.273 is equal to 0.956. From here we found beta 1 is 136.280 degree. So the answers are runner fan angles at periphery. Inlet angle is beta 1 161.634 degree, and at outlet beta 2 is equal to 15.748 degree. And at hub, inlet beta 1 is equal to 136.280 degree, and outlet beta 2 is equal to 32.456 degree. Thank you, sir.